Let's see. I turned on some buttons on the live. Good evening, everybody. We are live. I'm just getting started with a live session with you guys. Hopefully, many people will be joining very soon. Today, we're going to talk about active galaxies. Just to let you know, I'm going to share the live right now before people start to join and everything, because I always get distracted and I forget to share the live on my posts on the channel. So thank you so much if you're joining, and especially if you're going to be putting something in the chat in the live stream. Really appreciate in advance all the comments and incoming chat messages. And also, if you're seeing this later on as a video upload, please do leave a comment, and I always love to see those and say hi to you in the comments later on as well. Okay, so let me share the live before I forget. And let's just hope that many people will be joining us tonight, and we can chit chat a little bit, we can hang out, we can say hi in the chat, and then we can also talk about some interesting topics, of course, as always, including physics, cosmology, astronomy, and astrophysics. Today I picked out the topic of active galaxies because actually, I saw some questions in the comments. So I do read everybody's comments, and I respond to everybody's comments as well. As far as I remember, I try to respond to every single comment and everything. And I saw some questions about quasars, and quasars actually fall under the category of active galaxies. And so that is why we will talk about that tonight, okay? So who is here? Who is joining us? Let's see. Let me share the live and get that going. I have this on my other phone so that I can share it from there. How has everybody been doing? What are you guys up to? I'll say we are live. Heart, heart, heart. Evil eye remove. Sun, sun, sun. Win, win, win. And Steven! Oh my gosh! Hello, Steven. Hi, Jay Cook. Please do like, share, subscribe, and please do join us and say something in the chat. Really lovely to see everyone. Steven, how are you doing? Long time no see, Steven. How are you doing? Like and subscribe, my friends. Appreciate you. So I am looking forward to saying hi to everybody that joins. So Stephen, how are you? Jay Cook, how are you? Jay Cook says hi, hi Jay Cook. P2SODA, P2 Soda says hi, hi P2. 1eggs1 says salt, hi salt. And hi 1eggs. Skepter or Scepter Wolf says do a backflip. Hello Scepter. I just saw you were on live. I'm good. You. Thank you. I'm good. I'm recovering, and I'm here. Daydream Productions says I love buttered chicken. Oh, lovely. Me too. P2 Soda says he. Hi P2. Hi Melissa. Hi honey. Melissa Carnelia, or no, Melissa Carnella is saying OMG, you're so pretty. Thank you, Melissa. Thank you, P2SODA. Thank you, Daydream. Thank you, Steven, Scepter, Wolf, 1eggs. I'm looking at all your comments and usernames again to make sure that I didn't miss anybody. Steven is saying, I'm closer to publishing my book now. We're in editing now at the publisher. Oh my gosh, that's very exciting. Everybody, please do become friends with each other. So nice to see everyone. Thank you so much for being here and joining. And we will talk about some physics, and we will talk about some study with me themed topics. And today it's going to be active galaxies. But it's a fun chat. Usually there's a lot of people that join and become friends with each other and share things about their life with each other. So hopefully you'll have fun with that. Thank you, Daydream. Thank you so much. So let me look at the top fans right now. So the top fans, number 1 is Steven. Number 2 is Scepter Wolf. Number 3 is Daydream. Number 4 is P2 Soda. Number 5 is Fame Pace Taperil. Number 6 is Melissa. Thank you everybody so much. Please do like double tap on the screen to give us a like and say something in the chat. Thank you so much. Fame Paste Apparel is saying, I like your earrings. Oh, thank you so much. These are actually from my childhood. I got them years and years ago in Kolkata, India, where I'm from. What is your background education-wise? It is physics, physics, and physics. All my degrees are in physics, but thank you for asking. Soon I'll read book 3 as soon as I finish. Very exciting, Stephen. And I'm so excited, everybody, to see all the new usernames and new people that are on this live right now. Scepter, Fame, Daydream, Soda, and Melissa. So thank you. Thank you, thank you, thank you, thank you, thank you. I will be talking about active galaxies tonight. And your face is beautiful and your voice is very soothing to listen to. Thank you. I am so happy that you're here, Barry Bongs. What degrees and level, please? So my bachelor's with honors is in physics. My master's of science is in physics, and PhD is also in physics. And the subtopic that I did my PhD in is particle astrophysics. And I also did research in astrophysics and cosmology as well in undergrad and grad. I actually also worked in analytical chemistry, electrochemistry, and neuroscience in undergrad. But that was my undergraduate research. It helped me a lot to get into grad school. So thank you, chemistry and analytical chemistry and electrochemistry and neuroscience. And thank you, Somber's Lab. That's where I worked in undergrad. And I also did, so in undergrad, I was a double major in physics and chemistry. I ended up not finishing my chemistry degree, but I did physics, math, music. I also couldn't finish my music degree, actually. But I loved that in the US, you could take all of these things together. So then in undergrad, I was actually in a chemistry lab for a very long time, for like all of undergrad, like 4 years. I was working in this, more like 3.5 years, maybe. I worked in this chemistry lab, which was what I was mentioning, the analytical chemistry, electrochemistry. So a lot of people thought that I would go to grad school for chemistry because I did like chemistry a lot. I went to NC State for undergrad and Ohio State University for grad. Hi, Chris. Hi, Daydream. Hi, Scepter. Do you use AI, and if so, how? So I research, I use AI/ML for my research, and I also like develop machine learning algorithms for application in different research projects. So I would say I'm more of sort of in the research arena of AI/ML. So like developing algorithms to get something done, you know what I mean? That sort of thing in application in various jobs and things. So I've been using or working with AI and, you know, applying it and developing algorithms and whatnot for application in engineering and science topics for some years now. What instrument did you play? Violin. I played the violin. I also picked up the piano a little bit in undergrad because turns out that everybody in the US actually starts, well, I mean, not everybody, but it's very common to pick up the piano in classical music and then have other instruments that you also know on top of that. And then there were classes that you had to know how to play the piano. So even though my instrument was the violin, and playing with both hands with the piano was actually very difficult for me because I picked it up as an adult, you know, like as an 18 or 19-year-old in undergrad for the first time. I'd never played the piano before. So it was very hard, but I did manage to, you know, do what was needed there and pass that class. And I actually got an A- in that class. So I think I did pretty good. But I had an excellent professor for piano. She is Dr. Olga Klein-Kina, by the way. If you follow Western classical music, she actually performs live and whatnot. She's huge, she's famous, amazing pianist and performer. And that was the professor of that class. So I think she got whatever piano out of me that was possible. I think I could not read music, started on the violin, then the trumpet. I would never play either. Oh my gosh. Well, I loved reading music, actually. I wish that I had started sooner, and even now, I don't think that's an excuse. I think I should learn more and learn again. I'm at work right now. I didn't go to college. Hi, Snowkamoy. Hi, Chris. Hi, Snowkamoy. Hi, Steven. Hi, everybody. So yeah, anyway, that was the story of my undergrad. Thank you so much, everybody, for being here, and please do like, share, and subscribe the live and this episode if you don't mind. That would be very helpful to me. And also, there is, by the way, on YouTube, there's a new button that I think appears under videos. It's called hype, and people are able to hype the videos now for like a week or something to help smaller creators. So if you would be so kind to hype my videos, that would be really helpful to me. Do you need anybody to write code for you so that you can focus your entire mental bandwidth researching? Hi, B. Are you a coder? I actually kind of like writing code. It's a little, it's kind of meditative, if you will. It helps me to kind of calm down. Like, you know, the parts of the parts of a regular job, like meetings and I don't know, figuring things out and emails and communicating and client and all of that, you know, there is that. And then there is the coding part that you just do on your own. And I kind of like the on my own part quite a bit. But thank you so much. If you're a coder, then I definitely want some tips from you, and anything you share would be most amazing. What is your current focus in physics, astronomy? I'll do all the boring parts. Oh, actually, as far as computer science type of coding goes, and I actually do want to do a live stream here soon where I share my Python code with you guys about something. It's a simple problem that I coded up for black holes that I do want to actually go over, because you know the coding I do is really the coding that it's really like scientists and engineers type of coding. It's not like a computer science, like a hardcore computer sciencey type of coding. And so I do appreciate when people write very good software that then you know others can use. Like for example, I'll give an example. MATLAB is software that physicists and engineers use a lot. And then there's people who actually work on MATLAB. Like they actually create the software called MATLAB. So I absolutely appreciate B for coding. And if that's the type of coding you do, then thank you so much. I really don't like doing more of a computer sciencey type of coding. Like that's just not me. I like coding that you would need to do for analysis, for research, for like solving a problem. It's really like an analysis tool, probably is the best way to describe the type of coding I do. So I don't do coding that is like very, very, you know, I don't know, something that is software level, basically. So production level. My first instrument was flute. Saxophone. Oh, very nice. Wind instruments are really hard. I don't think I could do that. I finally figured out breathing while swimming, which was a big impediment for me when I used to swim earlier. I couldn't breathe and I couldn't hold my breath, blah, blah, blah. But now I can breathe while swimming, and that's how far I go, I think. Hi, Nusrat. Hello. I think I've seen Nusrat here before, so thank you so much for coming back. Nusrat B said you're stealing my heart. Yes, absolutely. I mean, if you want to talk about coding, you should tell us 10 more things about coding. I love that there are more and more technical people here talking about coding, music, sciences, and whatever, you know, anything technical is most welcome. I love it. When basic was the only background. Oh my gosh, I used to do basic. How did you know, Steven? When I was a kid. So did you learn coding in school? Yes. So in my primary school, like when I was really young, like probably from the age of like very young actually, we had to code in a programming language. I think it was called Logo. I might be misremembering that, but I have coded in a programming language called Logo, I believe. It was like, I don't even know, like I think it made shapes or something. And then I did GW Basic, Visual Basic, and I think in school, like in, you know, children's school level, that's all I probably did. Because in my 11th and 12th grade, I did Pure Sciences, which is basically physics, chemistry, biology, physics, chemistry, math, biology. It's like the PCM plus another one. You won't scare me off with production quality code. I don't think I write production quality code. I think I write code that can do research and analysis. So it's more like that. But I'm glad that there is people who are doing that. So anyways, then in undergrad, I did coding as part of research for physics and chemistry. You know, you always have to do coding if you're doing anything technical with any of the pure sciences. So in research and analysis, it's very common to do coding. And then of course in grad school, lots and lots of coding, lots and lots, C++, Python, those were my main languages in grad school. And then in work, I did Fortran. Actually, I learned Fortran in undergrad and I thought Fortran is actually used in physics. It's actually used a lot in astrophysics. All the star stuff is in Fortran because stars are old and Fortran is old. So that's the joke, is that it's not really a joke. I mean, stars are old and Fortran is old, you know. But basically I learned Fortran and I thought I might not ever use it again, but I actually did use it in my work, in my first few jobs. So Fortran, C++, Python, all of that stuff kept coming back in jobs as well and whatnot. Right now, I probably use Python the most. And the other day, like I was saying, I think what I'll do one of these days, once I figure out how to live stream and show my screen as well, because one time I live streamed and try to show my screen, and it was very slow. But I think there's some software that I can use which makes it go faster, like a streaming kind of thing. I'll help you work through the craziest Python code you can think of. Okay, awesome. So I think I should do a Python stream soon because I have a really cool problem that I want to show you guys. It basically proves that the smaller mass black holes are more dangerous to fall into than the larger mass black holes. So it's not that complicated because black holes are ultimately kind of simple as far as this type of math goes. And so I wrote something up in Python to kind of demonstrate that the smaller mass black holes are actually more deadly. And I plotted it up with to show you in terms of Earth gravity what the force, what the tidal forces on a person would be if you're falling into a black hole. And you know, for tidal forces, it's really that difference that matters. So like your height matters and your width matters, like your what's the word? Sideways tidal force versus stretchy tidal force, like the tidal force that stretches you out like a spaghetti. That's the tidal force because of the difference, because of the length between your head and your feet, right? So that's your height. So so I think I used like a 6-foot person. That's like, oh, thank you. I'm not afraid to roll up my sleeves and get my hands dirty, says B. Oh, very nice. Thank you, B. So this 6-foot person, I think I made the person 6 foot tall and 0.5 meters wide. A meter is like this. So actually, yeah, 0.5 meters is not bad for a person. So I think I made the person 6 foot tall and I made their width like 0.5 meters. And I showed the tidal forces on this person if you're close to a bigger black hole versus a smaller black hole. And then I even added a companion black hole. And so I've got some Python code on this that I want to show you guys, and I can work through, I can show the steps in both the code, because I know some people are interested in coding and they want to learn Python, etc. And also because this is a very cool, you know, it connects us with the physics topics that we talk about. So this is something I wanted to show you. Yes. Crazy sick wine. Hello, Drew. Hope you're well. I am. I'm recovering, and thank you so much. I'm here, and we're talking about coding and black holes. So I'm happy. Spaghettified simulator. Yes. So it's a simulation that shows the spaghettification and also the sideways force on the person, because what's this way called? Sideways tidal force. If there's another word, let me know. This way, the stretchy along your height way is called spaghettification. But if you're stretched also a little bit width-wise, then horizontal, sideways, whatever, that tidal force is also something to keep in mind. So both of those I have in there in that code. And it's a very simple, it's not a difficult, I just have it on a Jupyter notebook because, so by the way, I'm using Jupyter notebook a lot now because I used to code using whatever I, could find at the site where I was working, like, even Vim or whatever editor was there. And I think, PyCharm costs money, right? The IDE, but like Jupyter is free. And what I found now is that it's actually really nice to do the code lines and then show the plot and then do the code again and show the plot. And it actually works well when you have to share the code with people and sort of demonstrate something. So I thought of that and thought about showing that here as well so that we can get into a little bit of coding as well as physics. Before my dad, whichever one you're curious about will make it work. Okay, perfect. Thank you so much, everybody. Crazy Sick One is saying very good. I see. How are you doing, Crazy Sick One? How's everything going? Tell us something. Give us a little update for you guys, for you as well, Crazy Sick. And are you coming to MIT soon? Give us an update on that. Looking forward to hearing more. Can we get 10 likes? I think Baji just came into the room, Steven. So you'll see him soon. Let me share the live again. Okay, so without too much... Hi! Hi, Google. Hello, Google. I remember when you joined Rewrites History, my Google Mini, see, it's lit up. As soon as I said hi to you, my Google Mini over here has lit up, waiting for me to say something. And it's like, are you gonna ask me about the weather? Because that's what I do usually. So I remember you as well because you made my Hey Google go off a lot. Hey Google, don't worry. It's gonna. Okay, I won't worry. It's gonna continue to talk back to me. Did you watch the new Fantastic Four black hole scene? No. I haven't seen a movie in quite a while. Is there a new Fantastic Four movie and is there a black hole scene? Thank you. Tell me all about it. And Crazy Sick One also give us an update. I'm the real one. That one is the imposter, I swear. I love rewriting history. So, okay. So, love chit-chatting with everybody. And I'm going to come back and read all your comments very soon again. We'll take a quick few minutes here to talk about active galaxies because... Ooh, you start September 5. Oh my gosh. Are you coming into Boston? Do you have a place to stay and everything? Tell us more. So we're going to talk for a few minutes about active galaxies because some people have been asking about that. So hang tight. I've got this book. It is called Foundations of Astrophysics. It looks like this. It's a nice blue book. And it is written by professors, doctors, Barbara Ryden and Bradley M. Peterson. I actually got asked to relocate to Boston. Ooh, are you all coming to Boston soon? You should. I recommend it. So this is the book that we will be referencing tonight when we talk about active galaxies. And this is a topic that we have talked about before. And remember that our galaxy, the Milky Way galaxy, is a not active galaxy. It is classified differently based on its shape. It's a spiral galaxy. And we actually spent quite a bit of time on the channel a while ago, probably like months and months ago, when we talked a lot about galaxies. Like every single day we were talking about galaxies. And we saw how, based on Hubble, actually, very, important person in astronomy, we saw the classification of galaxies based on their shape, on morphology. So they were either spirals or elliptical or irregulars. So we saw a bunch of different types of galaxies, and we said that the classification of these is actually based on their shape. So you can imagine that the shape is not the end all be all for a galaxy, but back in the day, and it's not even that old, actually, the classification of galaxies is around 100 years ago, 100 years old. So literally around 100 years ago or so, people started to realize that there was actually a lot more galaxies out there than we imagined. The universe was a lot bigger than we had thought. There were a lot more galaxies than we knew about, and we started to be able to observe these and use observational data to really determine that, oh my gosh, the sky is a lot more interesting than we thought. There's so many more galaxies. And we started to see all these different sources. So sometimes these are called sources because ultimately a galaxy, it's a source of light. There is some luminosity about it. And if it has some sort of extension to it, it's not just a point-like source, such as a star, then it's a galaxy. But when you see the night sky with your naked eye, especially if it's a dark region where you're seeing the night sky, you see a lot of objects in the sky. Many of those are actually galaxies. They may look like a star, but they are actually a galaxy. But people started to do these observations. Hubble was very, very, he gave us path-breaking news about these types of things and gave us a whole new understanding of the magnitude of how very many galaxies there were, and also helped us to classify them and organize them into these categories based on shape. But then there are actually also some galaxies that are very different. They kind of confused people when people first saw them. People would see these objects in the sky and think that, what is this? Is this a star? What is this? What's going on? So these galaxies were kind of different, and you will see how they are very unique in a certain specific way. And this is something a lot of people have been asking about on the channel as well, which is, this has something to do with having a center of that galaxy which is very active. So you might have heard of AGNs, or active galactic nuclei, and basically something very explosive, very uniquely luminous is going on with the centers of these galaxies. But you might ask, well, even our galaxy, the Milky Way galaxy, has a supermassive black hole at its center. And even our galactic center is actually quite active. It's actually quite bright, right? But we don't categorize the Milky Way as an active galaxy, and you'll see why. So this portion of astronomy will focus on active galaxies or active galactic nuclei, and there are actually some types of active galaxies as well that we'll talk about. And you will see where these galaxies are quite different from our galaxy, the Milky Way galaxy, and also just other galaxies in general that we've talked about. Okay, so that's what that's what we'll cover tonight. Okay, so Crazy Sick said, yes, I have a place to stay. A nice condo. Oh, wow. Are you already in Boston? Liking the atmosphere so far. Oh my goodness. Could there be black holes between us and other celestial objects that block views of our galaxies from entire perspectives? Are active galaxies considered on the upwave of a crunch? So we will talk exactly what active galaxies are right now. And the other question I'll come back to, because it's very interesting. It actually, you should definitely, the quick answer is that you should look up gravitational lensing. So these different bodies that are, sometimes we call them compact bodies. So a black hole is an example of a compact body. It's not very luminous itself. Sometimes it's bright around the black hole because of things falling into the black hole, but the black hole itself is sort of this dark object, right? So such an object which has a lot of mass will act as a gravitational lens, actually. So sometimes having a black hole between us and other things is how we actually detect those other things, and it helps us with observations. Okay, so in astronomy, we make use of anything and everything. As you can imagine, in astronomy, the lab is kind of far away, right? Even if your object is the sun, it's still kind of far away. And if your object is the moon, it's a little, not so far away. But if your object is Mars, if your object is in a different galaxy, you can understand how your lab is kind of far away. So literally you would use anything and everything, and there's lots of different techniques that people use, and gravitational lensing is one of them. Okay, so if you like black holes, we will definitely talk about them as well tonight, and they will be part of this discussion. So let's see what the definition from this textbook is for active galaxies. And this is a textbook that is used to teach majors in astronomy and astrophysics. So you're getting an information from a good source, okay? So active galaxies have many distinctive attributes that distinguish them from the normal galaxies that we have discussed. So normal galaxies are what we belong to, the Milky Way galaxy. We're a very wholesome galaxy, but then there are these very different active galaxies, and we categorize them separately from the normal galaxies. So active galaxies actually produce large amounts of non-stellar emission, some of it non-thermal in origin, arising from energetic and violent processes. So a lot of emission that is non-stellar, and some of it non-thermal, is what actually makes active galaxies quite special. So we will see why, but here it is. Active galaxies produce more radio and X-ray emission than you would expect if all their light came from the photospheres of stars. Active galaxies have much of their light concentrated in a small central region known as an active galactic nucleus, or AGN. So this is the main thing, is that a galaxy has a lot of different objects, but if the majority of your luminosity is coming from your very small center, which is an active galactic nucleus, or AGN, then you're called an active galaxy. So we too, in our own galaxy, Milky Way, we too have we also have a galactic center with a supermassive black hole in it. It's very bright, etc., etc. Things are happening. Our galactic center is not boring. It's quite, exciting. But we don't categorize as an active galaxy because the majority of our luminosity is not coming from that source. We are wholesome. We have stars. We have other objects that are contributing to the luminosity. If the majority, so like literally, if most of your brightness is coming from your active galactic nucleus and everything else is kind of rivaled by that, then you would be categorized as an active galactic nucleus or active galaxy, okay? So light from active galactic nuclei is variable on short time scales. So it's also variable. It's not a steady source. So it's actually, that's another thing, it's literally active and unstable and variable, and things are happening, which are at these shorter time scales than you might think for a galaxy. But, here we are with these active galaxies. So, and it's virtually all wavelengths. So it's variable stuff happening, variable light coming out on short timescales at virtually all wavelengths. The timescale for significant variability is dependent on both luminosity and the wavelength, with the most rapid variability seen at shorter wavelengths in lower luminosity AGNs. So this is also, keep in mind what we have seen so far. This book is also current as of whenever it was written, right? So sometimes just keep an open mind to things changing as we find more and more objects and as we categorize more and more sources as either an active galaxy or a normal galaxy or spiral, whatever. Just keep an open mind, because it's after we have seen a bunch that we would be able to say these things. And in the beginning, like I was saying, this really confused a lot of people. So in low luminosity AGNs, X-ray emission can vary on timescale of minutes. So in some of these lower luminosity active galaxies, X-ray emissions even vary on timescales of minutes, which is pretty short. Some active galactic nuclei have jets that are detectable at X-ray, visible, and radio wavelengths. So this is crazy. Jets are coming out. Literally, AGNs are sometimes, there's those sort of artistic picturization of it. Sometimes have those jets, and those jets are not just in one wavelength. It's in like every wavelength. X-rays. Visible, radio, whatever. The jets contain, so fast radio bursts fast radio bursts are not necessarily just to do with these types of galaxies. It's more of an event. So I would call that more of a transient event in the sky. It may be associated with such a thing or not, but active galaxies are a little bit more broader than the fast radio bursts. If you know about gamma ray bursts, it's kind of, I like to compare it to that. Gamma ray burst is like a transient event in the sky that has to do with a specific event. And then fast radio bursts is like that, but in radio, So, but they're two very different things, and so I don't want to confuse you either. So some active galactic nuclei have jets that are detectable at X-ray, visible, and radio wavelengths. The jets contain ionized gas flowing outward at relativistic speeds. So these things have the very active galactic center, like I was saying, like there's obviously something very important at the center of these galaxies, just like at the center of our galaxy. But the big difference with these things is that these things, most of the luminosity of these galaxies come from that galactic center, versus for us, we also have a lot of luminosity, more luminosity coming from our stars. So that's where it's very different. And the ultraviolet, visible, and infrared spectra of AGNs are dominated by strong emission lines. So pretty much lots of emission in lots of wavelengths. It's very active, quite literally. So in order to be labeled, however, as an active galaxy, a galaxy need not have every attribute that we've been talking about. So it's not like, it's more like a choose any 3 out of the 5 proposition. Thus, there are many classes of active galaxies depending on which attributes a particular object displays. The accumulated evidence, so it might be a little bit of like, okay, does it have a lot of these features, and we call it an active galaxy. So most, if not all, bright galaxies harbor a supermassive black hole at their centers. So even our galaxy and a lot of galaxies that we know of harbor a supermassive black hole at their centers. So that alone doesn't make the galaxy an active galaxy, okay? Although bright galaxies contain supermassive black holes, not every bright galaxy is an active galaxy. A supermassive black hole is a necessary but insufficient condition for activity in galaxies. Maybe we could be study buddies. We are study buddies, aren't we? So basically, having a supermassive black hole is a necessity to be an active galaxy, but it is not sufficient to be an active galaxy. You also need to be a very crazy galactic center, which is contributing almost or most of the luminosity of that galaxy. So that's what make it an active galaxy, okay? The central black hole must be accreting gas sufficiently rapidly to have a luminosity high enough to compete with or outshine the stars in the host galaxy. So this central black hole of an active galaxy, so somebody had asked about this, so hopefully that person is here or we'll see this later. So yes, there is a black hole at the center of an active galaxy. There is also a black hole at the center of our galaxy, a massive black hole at the center of our galaxy. And in fact, there is a supermassive black hole at the centers of many, many galaxies that we know of. But that itself does not make it an active galaxy. What would be needed is you would have to have these crazy jets which come from stuff around the black hole falling into the black hole in such a tremendous way where there is lots and lots of emission from those infalling matter. We call them accretion. So basically this black hole is accreting material into it, and the stuff that's falling, it's moving so fast, it's moving at relativistic speeds, and it emits a lot of radiation, and this radiation can be at different wavelengths. Even in our own galactic center, we actually see radiation at different wavelengths. But if this emission from all of this stuff that's falling into the black hole is rivaling the luminosity, the emission from that, if that's rivaling the luminosity of the entire galaxy, then it's an active galactic nucleus. That's when we call it an active galactic nucleus. Otherwise, it's a normal galaxy. Even our galactic center is very bright. It's bright in X-rays, it's bright in radio. We actually, that's how these black holes give themselves away, right? Because black holes are black for the most part. Sagittarius A star is the name of our black hole, by the way. You have to have a little asterisk next to the A. So quite literally, it is called SGR A star, okay? Even though it's not a star, it's a black hole, but there's a bit of there's an asterisk after the A, just so you know. So basically, that's our black hole. It is also making a lot of things fall into it and making things bright around it because of that. Because when particles move very fast, they actually produce an emission because of different reasons, because of different physical processes, synchrotron radiation, those types of things, which can make the surroundings of a black hole very bright in various wavelengths, like X-rays or radio waves or whatever. But if this luminosity coming from the activity of this nucleus of the galaxy rivals the entire galaxy's luminosity, then we call it an active galaxy. Okay, so that's what we're dealing with here. So we can identify three major classes of active galaxies. So these are Seyfert galaxies, Seyfert, quasars, and radio galaxies. So I think somebody mentioned fast radio bursts. I'm not sure exactly if radio galaxies are always connected with that, but we will see. Seyfert galaxies and quasars are actually quite similar to each other. Seyfert galaxies can be thought of as a low luminosity, relatively nearby quasars. Radio galaxies are different in that their nuclear emission often is not prominent in wavelengths other than radio. We consider each of these three main classes below. The other thing I wanted to point out also is that I do believe that fast radio bursts, because somebody asked about them, is something that we, it's still considered more of a transient event, because I believe we have seen some in our own galaxy. So just by seeing a fast radio burst doesn't mean that the whole galaxy is an active galaxy. It's still considered just a transient event, if I'm not mistaken. So what is a quasar? So a quasar is a type of active galaxy. It is one of the types of active galaxies, so we will actually discuss that right now. We can actually jump to quasars right now, actually. Quasars are quasi-stellar galaxies or quasi-star galaxies. Quasar is short for quasi-star or quasi-stellar. And so quasars are very interesting. We will jump to it right now. And it's a type of active galaxy, the current topic of tonight. And somebody should Google fast radio bursts, but I do believe that they are a transient event. And you can probably see some of them even in our own galaxy. And the topic is kind of separate from this active galaxy topic, okay? Yes, type of signals. That's what I believe. That's what I believe. Like, it's basically like a transient event in the sky. You know, sometimes there is an event in the sky which is short-lived. It doesn't go on forever, basically. Like a star is a relatively stable source. Unless the star is going to die, you know, if a star were to say supernova, that could take some days to complete. So even a supernova is a transient event in the sky. I do believe that fast radio bursts are a transient event in the sky. Whereas when you talk about galaxy, it's a type of source that's there. You know, it's not going away. Like it's not like a bright spot that comes up and then it's gone within a minute or days or months. It's there. Okay, so it's a more permanent source. So ultimately in astronomy, there's all these different sources, right? All these different sources or objects. Object is the more general term because a planet is an object. It's not a source. A source would be something that makes its own light, probably. So that could be either a galaxy, it could be a star. But then there's also things that are called events. Event is something that is happening and then it's gonna be done and you won't get any more light from that thing. And that is called a transient event. For example, a supernova, a gamma ray burst, or I believe a fast radio burst, okay? That's why it's called burst. Burst of light, like a burst of radio waves, bursts of gamma rays, that sort of thing, okay? And if you want to talk about gamma ray bursts, that will take me a longer time because I actually kind of specialized in them. So I have a lot to say about gamma ray bursts. I don't know as much about fast radio bursts. So transient events are a favorite of mine. We can talk about that another time because I'll probably spend too long talking about it. There's a lot more to it than just the burst stuff that I said, but it's a transient event, okay? The end of a transit event sounds so sad. Well, transient events do happen in the sky, you know, like a supernova, you know, if we saw, for example, Betelgeuse supernova, we would be able to see that happening for at least, it could even be for months. But that too is a transient event. It will not be so bright after some time where we can't really see it. So things like that. Love that you love gamma rays. They're absolutely fascinating and terrifying. Yeah, so gamma ray bursts, as far as we know, happen very far, far away. They're definitely extragalactic type of events that we observe, of course. We've been observing since, I believe, the 60s or the 70s. And they were actually discovered during the Cold War. And people thought that they might be sort of things that Russia was doing against the US, blah, blah, blah. And the military actually discovered them, you know, but they ended up being transient events in the sky, which opened up a whole new type of astronomy. So that's gamma ray bursts, and I love gamma ray bursts, and we will dedicate another live stream to it. Now, let's talk about quasars. So, somebody asked, what is a quasar? Quasar is a type of active galaxy. It's not a star, it's not a transient event, it's not a gamma ray burst, it's not a NFRB. It's a galaxy. It's a whole galaxy, but it's a very special kind of galaxy, and we will talk about that right now. It's an active galaxy, and we know already from the definitions so far that an active galaxy is something that has a very active galactic center, which involves a supermassive black hole. But the special thing is that this black hole is making things fall into it so fast that the accretion is so crazy that the luminosity from all of that emission actually rivals the luminosity of the entire galaxy. So basically, it's a very, very active galactic nucleus. Part of that galaxy makes it an active galaxy. And a prime example or a category of active galaxy is quasars. And we will also talk about how they were discovered, because actually when they were discovered, and 3/4 quasar, right. When they were discovered, people were very confused because they looked to us like a star, like a point source. And that's why they are called quasars, quasi-stellar or quasi star or star-like. Okay, so people thought, are these stars? Like, because they're a distant source. You don't know exactly, right? Because you're not that close to it. People thought, are these stars? And then they were like, oh my gosh, these are not stars. These are actually a special kind of galaxy. You know, so has a bit of a history there. So radio telescopes first surveyed the sky in the mid-20th century. So, by the way, we have not been looking at the sky or observing the night sky in every wavelength always, right? So radio telescopes were not always around. The first time we started to have kind of radio telescopes surveying the sky was mid 20th century, so the mid 1900s. Okay, so once we started to have radio eyes of the night sky, for the night sky, we actually saw a lot more, right? Even in our own galactic center, the fact that we have the radio emission from the galactic center even in our own galaxy is because it's thanks to radio telescopes, right? Before that, we would not know sort of the beauty of our own galaxy as well in radio. These first surveys showed that the optical counterparts of most radio sources were galaxies. The radio galaxies discussed in this section. However, some radio sources did not have obvious counterparts in the optical, that is. So people pretty much were used to seeing, if they saw a radio source and they saw that it was probably a galaxy, they basically expected to see optical signals or optical emission from it as well. Pretty much. People were like, oh, we saw this in radio. Okay, turn on the optical telescope and we will see it in optical as well. Ambiguity arose because of the poor angular resolution of single dish radio telescopes. So people kind of liked to see it in optical as well. Once better radio positions were obtained, it was found that the radio sources were associated with blue star-like objects. So, what were these blue star-like objects? This was unusual. Stars are not generally strong radio sources. So everything that people knew about stars was a little bit confusing now, because people thought literally that these were blue star-like objects. They seemed very point-like. They seemed like pointy little things. So, you know, they were strong radio sources, blue star-like, but usually stars were not good or bright radio sources. It seemed clear that they weren't stars, so their star-like appearance led to the name quasi-stellar radio source, which was later contracted to quasar. So 3C273, by the way, is an example of a quasar, and it's one of the first quasars to be identified. So if you are ever interested, you can look up 3C273. It's a quasar, and we will also take a look at it tonight. I have a picture of it, okay? So note how when we see this picture, you will see that this 3C273 resembles the stars in the field of view much more than it resembles any galaxy. So if you look at the 3C273, it's literally a bright, it's just a dot. It's a source, it's a spot of light, but it looks like a dot. It does not look like an extended source, like what a galaxy would look like, a spiral or elliptical, like, you know, even in regular galaxies have some kind of extension to it, you know, once we focus in on it, right? Like the shapes of galaxies that people were familiar with, or even now what they expect is either a spiral looking thing, like either a fuzzy spiral, a fuzzy elliptical, a fuzzy irregular shape, etc., were basically what people are used to seeing. Here, we're seeing something that's a radio source. It looks like a blue-like point, like star-like thing. People were like, okay, this is some kind of source. Is it a star? But stars are usually not so strong in radio, but literally it just looks like a point, okay? So when the spectra of these quasi-stellar radio sources were obtained, things became more unusual still, so even more confusion. So they got spectra from it. The spectra contained strong, broad emission lines that did not correspond to any known element. So people were like, if it's a star, then we expect that there will be spectral lines that correspond to elements and things like that. You know, that's what we expect from a star. But here we have these strong, broad emission lines that did not correspond to any known element. The breakthrough to understanding what this was came in 1963 when Martin Schmidt had a eureka moment while looking at the spectrum of 3C273. So I will show you also the spectrum here, the spectrum of 3C273. I mean, this would be so confusing. Can you imagine? Usually when people think something is a star, and they're used to seeing the spectra of it, the spectral lines line up with elements and whatnot, and that's what people know and love. To see the spectra of 3C273, and it was just so confusing. That was a lot. So he realized that the emission lines in the spectrum were Balmer lines with a redshift Z of 0.158. No one had been expecting such a high redshift. So because the source was so bright, people thought that this must be kind of close, right? But it wasn't. It was so surprising, so surprising that when he figured out that this had such a high redshift, it corresponds to a radial velocity of 47,000 kilometers per second and a distance of 680 megaparsecs. The large distance was itself impressive at the time, but hardly unprecedented. Clusters of galaxies at redshifts as large as 0.2 were already known. So basically, the fact that you find a galaxy far away, that's not the point. That's not the issue. People thought it was a star, and it was really far. But it was also bright in radio. Like, all of these things were together very confusing. However, what was extraordinary was the luminosity implied by the large distance. So because people thought, again, that this must be some kind of star or something, because of its point-like nature, that bright point, people thought that this has got to be a star, but like it was so far away. Now, these emission lines are showing that, you know, this is actually at a very high redshift, which means it's very far away. But then, oh my gosh, the luminosity implied by that far distance is even more mind-boggling. Very large luminosity. Yes, you look at a pic of 3C273, it looks like a bright star. Exactly. It looks like a bright star, but it looks like a bright star. It looks like, once you realize how far it is, you're like, oh my God, that's a lot of luminosity. What the heck is this? Because they didn't understand what it was, right? They thought this was kind of like a star, quasi-stellar. Like a star that's really weird, I guess, because it was emitting in radio waves, and it also, the emission lines didn't line up with anything. But then they realized, oh, these are Balmer lines, and we can get redshift, and the redshift was very high, meaning that the redshift, meaning it was very far away. But then, how come it's so bright? How come we see this as so bright? That means that this thing has a crazy amount of luminosity. This is a crazy bright object. It's so far and still so bright, you know? This was very, very mind-boggling for people when they saw 3C273. Oh my gosh, they were like, wow, what is this? So what was extraordinary was the luminosity implied by the large distance. A quasar is an AGN, active galactic nucleus, that has a very high luminosity. So this luminosity is more than 10 to the 38 watts or so. The most luminous known quasars have luminosity of around 10 to the 41 watts, which is, by the way, in solar luminosity, that is 3 times 10 to the 14 solar luminosity. So in astronomy, we like to compare everything to the sun, which is our only star, in our own solar system that we know and love. And so 10 to the 41 watts of luminosity is 3 times 10 to the 14, 3 times 10 to the 14 solar luminosity. Or whatever, that's good enough. There's another example, but who cares? 3 times 10 to the 14 solar luminosity. So take 10 to the 14 suns, and times 3, that's the luminosity of this thing. 10 to the 14, okay, 10 to the 4, lots of zeros. The reason why they look quasi-stellar is that quasars are much more luminous than the sum of all the stars in the galaxies that contain them. So these galaxies have stars, but the the active galactic nucleus, I don't want to say quasar because quasar is the whole galaxy. Basically, the galaxy, the active galaxy that is this quasar, has other things too. It's just that the active galactic nucleus part of that galaxy is so much more brighter than everything else that it looks like a star. So isn't this the craziest way of finding a galaxy that is like a star, or something that looks like a star but it's actually a galaxy? Because its center is literally so much brighter than everything else, it looks literally like a point-like object or a point-like bright source or a star. We expect that type of thing to be a star. But in this case, we have found actually a very unusual or very different kind of galaxy, which is a quasar or quasi-stellar. Hi, Skeletor. Hi, B. Hi, Skeletor. Hi, Steven. Okay, so the reason why they look quasi-stellar is that quasars are much more luminous than the sum of all the stars in the galaxies that contain them. Thus, the quasars usually appear like unresolved points of light, just like stars. It's initially difficult to believe that the highest and lowest luminosity AGNs represent the same phenomena. So the highest as well as lowest luminosity of AGN is the same phenomena. Some of them are low luminosity, lower luminosity, and some of them are higher luminosity. There's a spread, sort of a spectrum of them, but it's the same phenomena. There is a crazy active galactic nucleus in all of them. So we will look at the spectrum and we will look at the dot later on. Indeed, as we'll describe next, the energy requirements needed to explain quasars were so radical, in the 1960s that a 20-year controversy. So this is a controversial topic. People probably debated this and argued about this quite a bit in astronomy. So there was this 20-year controversy over the nature of quasars. Are they high luminosity? So the question was, are they high luminosity versions of Seyfert galaxies at the large distances implied by their redshifts, or are they low luminosity nearby objects of some sort with their large redshifts due to some other effect than the expansion of the universe? Hi, Shakalaka, how are you doing? Hello, how are you doing, Shakalaka? Boom, boom. Someone's asking what's Virginia. So they were asking about these things. Either are they just really large distance away, high luminosity versions of Seyfert galaxies at large distances away, or is there something else? Like basically the luminosity implied by the very large distance away of the quasar gave people such basically such confusion. Their minds were so boggled that stop distracting. You're fine. Their minds were so boggled by the luminosity. Like, are they really that high of luminosity, or are they really that far away, that they started to question? It's almost like gaslighting themselves to see whether there was something else that might have been contributing to the implied high redshift. Like, is there some other thing going on here? Other effect other than the expansion of the universe, which would cause this thing to have such high redshift, as in it's so far away, and whatnot. Because the far awayness of it also implies the very high luminosity of it, okay? So for most astronomers, the matter was settled definitively in favor of the former hypothesis in the 1980s, with the detection of stellar absorption features in the faint fuzz surrounding quasars. The remarkable properties of quasars soon led to more efficient ways of discovering them. For example, quasars are very blue compared to stars. So the same thing that made them odd, once you know that this thing is odd or weird or unique in this way, then you just look for that weird thing more and more, I guess. So the remarkable properties of quasars soon led to more efficient ways of discovering them, thank goodness. For example, quasars are very blue compared to stars, so searches for objects with ultraviolet excess. So ultraviolet excess is basically this blue-likeness. Basically, if you, relative to starlight, we don't expect stars to have certain ultraviolet excess. So basically, we don't expect stars to be so blue. So if you see a star, that's kind of really odd and really weird and has ultraviolet excess, people were like, ah, that's a quasar. Okay, put that in the quasar bucket. So proved to be especially effective, the ultraviolet excess way of finding the quasars. Moreover, it quickly became apparent that there was an even larger population of objects that had the optical properties of quasars, but very weak, but were weak or even undetectable emitters at radio wavelengths. So this is where it gets even more interesting. There's a twist, more twist to the story. So hang in there, listen up. So basically, they quickly found out that there was an even larger population of objects that had the optical properties of quasars. So these were consistent with the optical properties or the visible wavelength light properties of quasars, but were weak or even undetectable emitters at radio wavelengths. These radio quiet sources became known as quasi-stellar objects, or simply QSOs. The original radio loud quasars make up only about 5% of the total population of quasars. So how weird that basically the quasars being radio sources set them apart. That's how they were discovered. So the radio loud quasars is how quasars just got discovered, period. Because if they weren't radio loud, and we wouldn't be confused about are these stars or not, then we wouldn't necessarily discover them, right? But turns out that actually there are radio quiet quasars as well. And in fact, the original radio loud quasars make up only 5% of the total population of quasars. So actually there are more radio quiet quasars than there are radio loud quasars. It's just that we discovered them the other way around. We discovered the radio loud ones first because those are the really weird ones. And the weird ones basically set off alarms about what are these things. So isn't that so crazy? Isn't that so interesting how things get discovered? The more weird you are, chances of discovery is maybe higher. So intensive searches for quasars turned up yet another variant of the AGN theme, objects that are known as BL-LAC objects. So these are BL, like the two letters B and L. And then LAC, LAC objects. I'm not sure if the loud ones will become quiet at some point. Unlike Seaford galaxies, which are named after their discoverer, BL-LAC objects are named after their archetype, BL-Lacertae. The name BL-Lacertae is the type of name, 2 letters plus the Latin genitive form of the constellation name that is given to a variable star. So by the way, we have talked a little bit about variable stars before. These are stars that are very variable, that are very different than regular stars. There's a lot going on at short timescales with these stars. So in fact, BL-Lacertae was originally thought to be a variable star within our own galaxy. However, deep exposures reveal that BL-Lacertae is not a star, but a distant elliptical galaxy. Its redshift is 0.07, puts it at a distance of around 300 megaparsecs. So this thing, maybe that's why there's more. Yes, I mean, it's ongoing. There's definitely more to find. The reason why Bia Lacertae was originally mistaken for a star, so another example that was mistaken for a star, which is different from 3C273, which is a quasar, is that it was unresolved. Its unresolved nucleus is brighter than the diffuse fuzz of starlight surrounding it. The nuclei of Bia Lac objects are rapidly variable and have a non-thermal spectrum. So one more interesting thing here, non-thermal spectrum, rapidly variable, but do not show any emission lines. So now, as opposed to 3C273, now we don't have emission lines. It's just crazy. It's just like these are crazy things, you know, in astronomy that we're finding. This makes it difficult to determine this distance to a Bielac object unless you can manage to detect the absorption lines in the fuzz of starlight. Doing so is very difficult for many Bielac objects since their nuclei are so extraordinarily luminous compared to their stars. So once again, the nuclei is very, very much more luminous than the rest of the galaxy, the rest of the stars and everything. But in this case, it's got some other features like the rapid variability, non-thermal spectrum, and the lack of emission lines. So it's difficult to get any absorption lines because it's extraordinarily luminous compared to the stars. It also, from the fuzz, that is, it also makes it difficult to determine their morphology. It's conjectured that all Bielac objects are elliptical, but no one is totally sure because exactly what these objects' shape is. I mean, if you could see the fuzz of the starlight around it, then you would be able to say something about the shape. But if that fuzz is very difficult to see because of the center part being so bright, and it being so far, etc., then it can be hard. The flux from a Bielac object can change significantly. The other thing, what is more, is that it's very variable. So the flux from these objects can significantly differ or change from one night to the next. This indicates that the bulk of the luminosity comes from a region less than 1 light day across. Wow, that is 200 astronomical units, where an astronomical unit is the distance between us and the sun. So these things are very variable. If you figure out exactly what the time scale of the variability is, then you can even say, oh, this means, I mean, most of the flux we know is coming from its center, and that flux is changing from one night to the next. Like tonight, some flux, tomorrow night, another flux. Wow, that is a lot of variability. This indicates that the bulk of the luminosity comes from a region less than 1 light day across, which is pretty short for a galaxy, because remember, this is a galaxy, and the bulk of its flux or the bulk of its luminosity is coming from a region that is 1 light day across. That is so short, and I'll give you some comparison number. Our galaxy, the Milky Way galaxy, is 100,000 light years across. So for a galaxy to have its main activity going on within a light day across is actually, that is very unique. That is very unique. Very, very unique. Like, we have a wholesome galaxy with all these stars, objects. We have a supermassive black hole. We have so much stuff going on. But our luminosity, first of all, is not varying like crazy. And second of all, it's not the main stuff that is creating luminosity is not 1 light day across. It's more like 100,000 light years across. So, that's not really the case. I'm sure basically our halo is a lot darker, right? So I don't mean to say that the whole galaxy is equally bright or anything like that. Even in our own galaxy, most of the luminosity of our own galaxy is pretty close to the center. So our halo is a lot darker, etc., etc. We can talk about our own galaxy as well in detail. But this galaxy has all of this crazy stuff happening. The bulk of the luminosity comes from a region less than 1 light day across. That's still very short in terms of a galaxy. So anyways, Seyfert galaxies were first noticed because someone looked at images of spiral galaxies and said, wow, those nuclei are really bright. Bielac objects were first noticed because someone looked at the radio emission from Bielac-Rete and said, wow, that's way too much radio emission for Bielac-Rete to be a star. So this is how some of these things were discovered. That's the end of that section on quasars. We can also talk about radio galaxies and Seyfert galaxies. I kind of jumped to the quasar section. So active galaxies, there are like a few different types. These are Seyfert galaxies, number 1, number 2, the quasars, and number 3, radio galaxies. We kind of talked about just the quasars right now. But because of the weird characteristics of quasars and being radio loud, the high redshift, etc., is how it was discovered. And then we found another whole population of quasars that were actually radio quiet. And then we also have these Bielac-Rete objects, which have variability on top of all of that and whatnot. So that's what I have for you in terms of quasars tonight. Any questions? And we can also talk about our own galaxy. So I wanted to real quick touch upon, this is actually how we know that we have dark matter in our own galaxy. Had we maybe observed the same? That's an interesting question. I think I'm not exactly sure the sample of quasars that they would be working with, but I'm sure that they would want to sample something with angular diversity. So how you know that you're not just looking at the same source again is by looking in a different direction. So astronomy does give us different directions. So you can have angular diversity as well, okay? So you don't have to keep looking in the same direction to find newer and different things. How did black holes what? So I wanted to talk about, like, real quick, because we just now talked about luminosity of these active galaxies, I wanted to touch upon our own galaxy. Oh, here we are. Our galaxy is also talked about at length in this book, if you're ever interested. So, let's real quick. I wanted to talk about, I wanted to find the part where we, angular diversity is a new term for me. Thank you. Of course, absolutely. So something that does not change. So the topic that we've been talking about in previous lives, for a few lives, cosmic microwave background radiation, CMB. That is something that does not change at all. If you look in all different directions, like you could look at the sky this way, that way, and you still see the CMB as being very homogeneous and isotropic. So the CMB is an example of something that does not have angular diversity. You'd have to look at with very much high resolution and precision to see little variations in the CMB. So that is a whole another topic that we do also discuss on this channel, and that gives us things to think about and things to learn in cosmology. But with respect to the quasars and Bielacertae objects and other, all these things that we're talking about, we can definitely utilize angular diversity. So let me look real quick. I always let's see. So here they're talking about Sagittarius A. So at the center of our own galaxy, the Milky Way, how did massive black holes form in the centers of quasars so early in the universe? That's a great point. So I'm not exactly sure, but I'll just say this, that black holes are originally black holes are stellar remnants, right? So you need a star to live and die to make a black hole, right? The stars live and die to become either a white dwarf or a neutron star or a black hole. So in a sense, a black hole is just a stellar remnant, but then a black hole can get bigger over time when it eats more and more things from its surroundings. And so no black hole starts, I would like to think that no black hole starts as a supermassive black hole. It becomes a supermassive black hole over time. So just from that logic, I think that these were like stars at some point that died, became a black hole, started to eat stuff, had the opportunity to eat more and more, and became supermassive black holes. And the jet activity, like, depending on the configuration, if this infalling matter is, traveling at relativistic speeds and emitting all of that radiation and basically rivaling the luminosity of those galaxies, then it falls under this active category. So in a sense that these active galaxies are not that different really from us. It's just that our galaxy, I like to think, is just more wholesome. There's other things going on in our galaxy, like stars, lots of stars, that also contribute to the luminosity. And our galactic center is not so bright where it would rival the luminosity coming from all of those stars. Hey, Miss Beautiful. Oh, hi. Hi, Meti Grandong. Hello, Meti. How are you? Primordial black hole seedlings. So primordial black holes is something that we discussed very briefly from Stephen Hawking's book. I believe that Stephen Hawking was looking for primordial black holes. And I'm not sure exactly how much progress he made. So I don't know too much about primordial black holes. I think that's a topic that is sort of an open question, and I personally don't know a lot. But I think he was trying to find them and whatnot, and I think he might not have had a lot of luck, is if I'm remembering correctly from Stephen Hawking's book. So I'm not sure, right? Like, I'm not really sure how these quasars or us even ended up with a supermassive black hole. But I would imagine, just from the physics of what we know, is that why would anything ever... So somebody said, this gives me hope that one day I too can become a supermassive. Yes, you can. So this is the important thing to note about black holes, is that yes, even you can be a black hole. This is what I love about black holes, is that a black hole is nothing but a massive object that has been compressed to a Schwarzschild radius. So the physics of black holes, at least classically speaking, is incredibly elegant and simple. So if you just compress something with mass down to a tiny, tiny radius, which we call the Schwarzschild radius. Schwarzschild is a guy who did this math and gave us this physics. If you just compress something, like a black hole is nothing but a compact object, right? Like we have stars, and then we have stellar remnants, which are nothing but compact objects. And why is it a compact object? Because a star collapsed under its own gravitation because it ran out of fuel, right? So when it's a star and it's burning like a star, then it has nuclear power, but when it runs out of fuel, it collapses under its own gravitation. So if you collapsed under your own gravitation and compressed very, very tiny like, then you could also become a black hole. Everybody has the potential to become a black hole, but it's a little bit more practical for stars because they have a lot of mass and the collapse can be much more extreme. It's more possible for a star's collapse to be that extreme. And the Schwarzschild radius for a star is not that tiny. The Schwarzschild radius for you would be very tiny. It might be something that is a little impractical to attain, but the Schwarzschild radius for a star, which is a much more massive object than a person, is a pretty practical, attainable radius. And at some point when it was theorized, when black holes were theorized, people didn't expect them to actually exist in nature, in the wild. But guess what? Then neutron stars were discovered at some point. And that gave people a lot of hope that maybe black holes were real too. Because when black holes were theorized, I mean, Einstein, Schwarzschild, all these guys never expected a black hole to be real. But a black hole is not only real, they are absolutely there out in the wild and in nature, right? So they didn't think it would be a thing, but it's definitely a thing. But when they discovered neutron stars, and those are pretty compressed as well, they're like the size of Manhattan. So that gave people hope that, oh my gosh, if something can collapse down to the level of a neutron star compactness, then maybe we can also become a black hole for stars. So yes, absolutely. Oh, of course. Yeah, anybody can become a black hole. So in physics, we don't like to say things are impossible, especially when, it's supported. The physics is absolutely supported for you to become a black hole. Yes. You just have to be compressed enough down to your Schwarzschild radius. And everything with mass has a Schwarzschild radius, which I love. This is the type of classical physics I love. Any massive object. Earth has a Schwarzschild radius. The sun has a Schwarzschild radius. You have a Schwarzschild radius. Stars have a Schwarzschild radius, and stars are much, much bigger, massive objects, so their Schwarzschild radius is a pretty practical length to attain. So because of, all someone has to do as a star is to be compressed down to its Schwarzschild radius, that's how we get a black hole. So I imagine that any black hole started off as a stellar remnant, literally the remnant left behind by a star after its death. And after eating more and more and more, it became a supermassive black hole. So that's what I would think. I'm not sure. I don't really know of any other way. Yes, thank you. We will talk about Sagittarius A star next time. Because you guys brought up our galaxy and Sagittarius A star, and it is a very interesting topic, but I think we will talk about Sagittarius A star, which is our own supermassive black hole. We will talk about that next time. How about that? Maybe tomorrow. Maybe I can try to go live tomorrow. Any other questions, comments? love, hate that you want to express? Did you like and subscribe? I wonder if there's a higher dimensional radius that we haven't. Well, there are definitely higher dimensions that hopefully we see you more often. Thank you. Well, there are definitely higher dimensions that are required by string theory. We actually talk about that a lot, B. Is that the type of dimension you're talking about? So we actually talk about extra spatial dimensions, aka higher dimensions that are not only suggested or proposed, but required by a ground unification theory candidate, which is superstring theory. We've actually been discussing that a lot. If you see my shorts and videos and previous lives, we've talked a lot about this. Higher dimensional lattice, yes. So yeah, so the higher dimensional topic is something that also we come back to. It comes up quite a bit, but basically this thing about us not knowing everything and not having a good way of unifying gravitation with the non-gravitational fundamental forces. No, of course not. Higher dimensions are not crazy at all. Quite mundane, depending on who you talk to. So, you know, this issue that we have of a lack of unification of gravitation. Oh, there's Baji. Lack of unification between gravitation and the fundamental non-gravitational forces leads us to attempt to have a theory or something that can perhaps and mayhaps unify them. And a candidate for such a thing is superstring theory. And superstring theory doesn't just lightly suggest or propose higher dimensions, more dimensions. It proposes 6 extra spatial dimensions depending on which theory. I think M theory has 7, so there's like 3, or sorry, not 6. What am I saying? 3 plus 6, 9. Oh, no, I said the right thing. It's 3 spatial dimensions like usual, time, and then 6 more in superstring theory, and I think 7 more in M theory. So total superstring theory is either 10-dimensional or M theory is 11-dimensional. So the higher dimensions you asked about is required in superstring theory. So those guys all believe in it thoroughly. Is it okay if they cannot be unified? Oh, that's a great question. That is actually a very pertinent question. You know, given how much that is an excellent question. I think this might be one of the best questions I've ever got. Is it okay if gravitation is not unified with the 3 fundamental forces, the other 3? That is a great question. Given how complicated superstring theory is, and given how much it complicates things to unify gravitation with the 3 non-gravitational fundamental forces, one might want to give up and be like, hey, maybe they cannot be unified and maybe we just live with that, you know? And also, the other thing is that maybe gravitation is kind of fundamentally different. It's not, in general relativity, it's not even a force, right? Oh, you like the kitty. That's Baji. Thank you. Kingsman is saying most beautiful thing in the world. Thank you so much. There's Baji Baba. Thank you so much. So in general relativity, gravitation is the curvature of space and time. It's the fabric of space and time. It's not even a force, actually, right? In general relativity. So there are people that probably do advocate that we don't think of gravitation in the same way. And I mean, we don't. We can't. We don't have a, their food is getting served. Sachi, mama. Sachi. I have to invite Sachi to come and eat her snack. Sachi, mama. Yeah. Come, Sachi. Come, Sachi. Ashushana. Tumyo khao, babu. Actually, give me 1 second. I need to, maybe I'll show you guys the kitty cats. I need to place their bowl because Baji's otherwise eating everything. 1 second. Here you go. Sachi, come. By the way, guys, how is the audio? Hi, Steven. Hi, Kingsman. How is the audio of tonight? Did you guys, audio is good. Oh, good. Did you guys like, share, and subscribe? Oh, thank you. Hi, Turkey. Turkey, are you from Turkey? Hi, Steven. Hi, B. Are you from the Turk? Oh, how is Turkey? Please do like, share, and subscribe. Thank you. Especially please like and subscribe. Can we get 20 likes? Turkey, are you really from Turkey? That reminds me, I should breathe a bit now. Let me know any last questions you guys have, or let me know any last questions, comments, loves, or hates that you have for me. I will do some deep breaths and read your comments. Oh yes, if you want to become a member, you should do so. That's one way to support me. Also, you could do a super chat. Oh, thank you, Crazy. RYGU. Hi, Rigu. Unify what gravity? Yes. Yes, we were talking about whether it is worth it or whether it makes sense to try to unify gravitation with the other forces, because as we kind of know, gravitation is very different from those other forces, and there have been a lot of challenges, a lot of complications. Superstring theory is the candidate for that unification, but it also ends up proposing all these extra dimensions, which are completely fine for some people. Some people find it quite mundane to consider extra dimensions, and some people find it to be not really acceptable if they cannot be probed. Yes. Whether it's okay to not unify them is actually a really brilliant question that I think I'd have to um, think a lot more about, because that is that is a that is a good that is a good question indeed. Whether it's just okay to not unify them. Because I believe we kind of talked about this a little bit, where even if we did unify them, there would still be, it's not necessarily the end all be all of understanding nature. Or maybe it is. I don't know. Like, I don't know if making things so complicated and having all these equations to then unify something in a very geometric kind of way, like which is what string theory is, really provides the extra insights that people might have been looking for when they were trying to unify the four forces. So, and I say four forces with the caveat that it's four forces in particle physics. In pure general relativity, gravitation is actually not a force. Okay, keep that in mind. Any other questions, comments, thoughts? Thank you for not laughing at my question. Of course. These deeper questions are actually very legit. I went swimming today. Makes me sleepy. Meorana, thank you for all you do. That's all I gotta say. Thank you, Crazy. So you're already in Boston? Which part of Boston are you in? If you don't mind, are you in Cambridge? You already moved? Do you miss California? I want to know all about this move. Good night. Roxbury. Wow. Well, Crazy Sick One, welcome to Boston. I'll catch up with you guys next time. Welcome to the live. Thank you for chatting. Thank you for being around for the Physics Live and for dominating the chat during this enjoyable live stream. I liked it. That dude totally got pulled out of our timeline by time patrollers. Oh, wow. Thank you for liking, sharing, and subscribing. And for double tapping and giving us some likes. Thank you so much. Headed to Cambridge next week. Wow. I love Cambridge. You should definitely check out the Harvard Art Museum, some food. Oh my gosh, the fall is gonna be so pretty. Do you like the weather? It was rainy today. Oh my gosh, we're in the same weather now. I can talk about Boston tidbits and you'll actually relate. Oh gosh. Baji. Baji's over here. Did you like the rain? It was so rainy today. Do you have a car? We should talk about parking next time. What do you have planned for this? What do you have planned this week? Anything special this weekend? We could unify them if we find graviton. Yeah. The search is on. This weekend, I think I'm going to a party. Hi, Baji. Baji wants to say hi, guys. Come, Baji. Did you hear him? Baji, say hi. Hi, Baji. Baji, do you want to come on this side? So you have a car, so we should talk about parking. Formidable. Baji's on a diet. Oh, hi, Baji. Oh, Baji. Oh, Baji's nails are getting long. If you have a car, I don't know what you'll do with the car in Cambridge. Cambridge is not very car friendly. Stop it. Ah. Do you have parking in your condo? Cambridge is not car friendly. I'm just gonna tell you now. But I want to do the beach. I've been doing the beach like every week. So this weekend, let's see. I think I'll do the beach. Maybe see my friends. Something like that. What are you doing? Thank you for liking. Yes, I have parking. I enjoy walking as well. Yes, I have parking. I enjoy walking as well. Yes. If you enjoy walking, you're in the right place. Boston area is good for walking. You should check out the Fantastic Four. Okay. Black hole scene. I don't know how to pirate movies. I don't do that stuff. I pay for my art. I don't pirate. I don't know how to do that. And I also, I don't think I have any streaming services right now. So, but maybe I will at some point. Just unpacking, maybe go out, have a few beers. You know, any good spots in Cambridge? Oh my gosh, well, there is a lot. I mean, Cambridge has a lot of good spots. Let's see, there was, honestly, I went dancing in Cambridge at some point. Was probably one of my like more fun nights in Cambridge. Was like bars or clubs where there was a lot of dancing going on. So I don't remember exactly how the drinks were because I was busy with the dancing part. And we were just going from place to place to place. And so I didn't even see the names of these places. Like, you know, but this was a while ago. This was when I was kind of new to the Boston area. And at this point, there is definitely, okay, I don't know about beers, but let me just tell you about this sandwich place that I have been meaning to go back to or go to in Cambridge. Because I've gotten sandwiches delivered from there, but I haven't actually eaten there. So you should check this out. This is called All-Star Sandwich Bar. It's a sandwich bar with all kinds of sandwiches. And I mean, I like my food. I like a lot of different kinds of food. But right now, one of the things that is intriguing me is actually the sandwich bar and all the different types of sandwiches there. And I've gotten sandwiches delivered from there, and it's really good. A really good grilled cheese, comfort sandwich. So you should definitely check out the food in Cambridge. I don't know, I'm sure they have good beers a lot as well everywhere. Are you sure it's All-Star and not All Quasar? Great question. It is called All-Star Sandwich Bar. You should go there. You should check that out. And also they have Indian food. They have all kinds of good food in Cambridge. Have fun with it. Have fun with it and let me know more questions. We should definitely talk about Boston area more. And let me know how it goes, how it's going for you. I'll definitely give it a try. Sounds good. Oh, very nice. Oh, it's party time. It's party time. So definitely let me know how it's going for you guys and enjoy. And I'll see you next time, okay? Thank you. Thank you for being here. I'll see you next time, hopefully tomorrow. Bye. Thank you. Bye. Have a good night. Thank you for the likes and the loves and the please do subscribe and like, share, comment. And if you're seeing this as a video upload later on, please do leave your comments. I really love looking forward to seeing all your comments in my other videos, shorts, all that stuff too. So everybody, please do continue to show some love and leave me some comments in all the videos and shorts. Good night to you and Baji. Thank you. Good night to you guys. Thank you so much. Good night. Sleep tight and bye-bye.